Today we shall discuss the physical chemistry of first B.Sc. In that physical chemistry, we shall discuss in detail indicators. Indicators are organic substances. Generally, they show different colors at different conditions. Especially in case of acid-base titrations, these indicators, they show different color at different pH. So, we shall discuss today types of indicators, theories of indicators and pH titration curves mainly we shall discuss today. First is types of indicators. Generally, indicators can be classified as acid-base indicators, redox indicators, adsorption indicators, like so many types of indicators are there. Examples for these acid-base indicators: phenolphthalein, methyl orange, methyl red, parathymal blue. Similarly, for redox indicator, we have diphenylamine. For adsorption indicators, we have eosin, fluorescein, etc. These indicators, they are used for different reactions, different titrations, where the titrations, acid-base, redox or adsorption titrations are involved. Now, there are two theories which explain the indicator action, the reaction of indicators in different titrations. First theory is Ostwald's theory. Ostwald's theory explains how these acid-base indicators, they act in a titration. For example, if you take phenolphthalein, phenolphthalein is slightly acidic, it is an acidic indicator, whereas methyl orange is a slightly basic indicator. For example, if you take phenolphthalein, it ionizes in solution to form H plus and anion of phenolphthalein pH minus. So, it ionizes to form ions. Similarly, methyl orange, which is slightly basic, it ionizes to form a cation and hydroxide ion. The theory says that the ionized form has got different color when compared to unionized form. So, this ionization takes place at a particular pH range. Now, when this phenolphthalein ionizes to form H plus, when you titrate an acid with a base, for example, HCl with sodium hydroxide, HCl reacts with sodium hydroxide. After neutralization, it liberates OH minus. This OH minus combines with H plus to form H2O. H2O is feebly ionized, it forms H2O, whereas NaOH ionizes strongly Na plus and OH minus. When that OH minus is consumed by H plus, phenolphthalein anion combines with Na plus, it is highly ionized. So, this is highly ionized when compared to water. Therefore, this phenolphthalein which ionizes in solution, it has different color, anion has different color when compared to unionized form. And this methyl orange, similarly, methyl orange ionizes to form a cation and hydroxide ion. So, when you titrate a weak base against a strong acid, this Me plus and OH minus combines with H plus to form feebly ionized, and Me plus it combines with the anion which is highly ionized. Therefore, this ion has got different color when compared to unionized methyl orange indicator. As I told you, this water is feebly ionized. So, we can express this pH range of an indicator by considering this equilibrium. Water is feebly ionized, therefore, we can apply the law of mass action to this equilibrium. If the equilibrium constant is K, we can write according to the law of mass action. Equilibrium constant K is nothing but the product concentration, H plus concentration and OH minus concentration divided by the concentration of water. Since water is feebly ionized, the concentration of water is almost constant. Therefore, you can multiply these two constants, equilibrium constant K and this is also a constant. These two constants we can represent it by Kw. This Kw is called ionic product of water. Ionic product of water is nothing but the product of H plus concentration and OH minus concentration. Pure water is very weakly ionized. At 25 degrees centigrade, its concentration is 10 to the power of minus 7. Concentration of H plus is 10 to the power of minus 7, and concentration of OH minus is also 10 to the power of minus 7 at 25 degree centigrade. If you multiply these two, you will get 10 to the power of minus 14. Therefore, Kw value is 10 to the power of minus 14. Since it is a very small quantity, 10 to the power of 7 minus 7 or 10 to the power of minus 14. Since it is a very small quantity, we can convert that into a whole number by taking logarithm. Therefore, by taking logarithm to the base 10, we can convert these small values into a whole number. Therefore, minus log Kw is equal to minus log of H plus ion concentration minus log of OH minus ion concentration. So, this minus logarithm of a constant of a term is represented by P power of Kwp. Therefore, this is Pkw minus logarithm of Kw is Pkw minus logarithm of H plus to the base 10. So, to take logarithm to the base 10 minus logarithm of H plus ion concentration is pH, and similarly minus logarithm of OH minus concentration to the base 10 is POH. Therefore, this Kw is the sum of pH and POH. pH is 7 at 25 degree centigrade and Pkw is 14 at 25 degree centigrade. Therefore, Pkw is equal to pH 7 plus pH 7 plus 7. So, therefore, always it is 14. pH plus POH is 14. Suppose if pH is more than 7, if it is more than 7, then you have to find out the value of pH by subtracting it by 14. pH is equal to 14 minus POH, or POH is equal to 14 minus pH. Therefore, by knowing pH or POH, other term can be calculated. So, this pH is the hydrogen ion concentration of pure water, but in case of indicators, in case of titrations, pH varies, it varies. So, therefore, we have indicator constant that is related to indicator range. First, let us know what is indicator constant and we shall relate that to indicator range. Indicator constant, indicator is also a weak acid or a weak base, as I told you earlier. Therefore, this indicator ionizes and it forms an equilibrium. Because it is a weak acid or a base, it ionizes to form H plus and In minus if it is an acidic indicator, or it ionizes to form Me plus and OH minus in case of methyl arate. Therefore, indicator you can apply the law of mass action, the equilibrium constant Kin, let us represent it by Kin. Kin is equal to concentration of H plus ion and concentration of indicator ion divided by concentration of Hin. Therefore, let us calculate the pH of this indicator by taking H plus. We can rearrange this expression. H plus is equal to Kin into concentration of Hin divided by In minus. So, this H plus concentration, as you know, if you take minus logarithm, negative logarithm of H plus ion, that gives you the pH. Therefore, take minus log on both sides, minus log to the base 10 on both sides, minus logarithm of H plus to the base 10 is nothing but the pH, minus logarithm of Kin to the base 10 is nothing but Pkin. If you take negative logarithm, this becomes negative logarithm of Hin by In. If you convert that into positive form, this goes upwards and this comes to the denominator. Therefore, this becomes logarithm of indicator ion divided by logarithm of unionized indicator. This ratio In by Hn, it may be H by 10 by 1 or 1 by 10 depending upon the indicator. So, if you take the ratio, if the ratio of ionized form of the indicator and unionized form is 10 by 1, it becomes a logarithm of 10 to the base 10 is 1, or this is minus 1, plus 1 or minus 1. So, plus 1 or minus 1. So, this pKin indicator plus or minus 1 is the indicator range. 2 units of pH. So, 2 units of pH. For example, in case of phenolphthalein, the indicator range is 8 to 10, 2 units. In case of methyl orange, in case of methyl orange, it is between 3.5 to 5, like the 2 units of range is there, that is pH range. So, at that pH range, these acid base indicators, they show different colors. Therefore, by knowing the pH, we can find out the color of the indicator. So, therefore, the color of the indicator depends on this ratio, unionized indicator divided by ionized form. So, this ratio, it may be 10 by 1 or 1 by 10, that gives you different colors. So, this is the pH range. pH range, so this is the relationship between indicator constant and the pH range. So, this is about Ostwald's theory. Ostwald's theory, which says about the ionization, and it says that an acid base indicator is either a weak acid or a weak base. So, the theory says that unionized form has got different color than the ionized form, and this ionization takes place with a range of 2 units of pH. So, therefore, the first theory, Ostwald's theory says about this thing. There is one more theory, second theory, that is called quinonide theory. This quinonide theory says that acid base indicators, majority, all of the acid base indicators, they have one or more benzene rings. These benzene rings, these aromatic rings, they undergo oxidation, they undergo structural change to form quinone form, quinonoid form. So, this is benzenoid structure of the indicator. This is the quinonoid form of the indicator. When the pH changes, this benzenoid aromatic ring becomes non-aromatic ring. This benzenoid structure is non-aromatic. Therefore, the theory is quinonide theory. Quinonide theory says that indicator assumes 2 structures depending upon the pH range. This is benzenoid form and this is quinonoid form. For example, if you take the changes that are taking place in case of phenolphthalein, it is aromatic in nature. There are 3 aromatic rings. So, in presence of a base, strong base, the structure changes. So, here actually we have to write a phenolic group. This phenolic group undergoes oxidation, removal of hydrogen undergoes oxidation to form this quinonoid form. This is benzenoid form, and this is quinonoid form. So, in the what the theory says that in the quinonoid form there is continuous conjugation of pi bonds. Actually, here you see 1 pi bond, 2, 3. So, 3 pi bonds are conjugated to each other. When there is conjugation of pi bonds, they form a pi cloud of electrons. These pi cloud of electrons, they absorb and they emit radiations in the visible region. That is why they are colored. These indicators are, majority of them, they are colored because of the formation of quinonoid form. In the quinonoid form, there is conjugated pi bonds. These conjugation pi bonds forms a pi cloud. This pi cloud absorbs and emits radiation in the visible region. That is why they are colored. So, the theory, majority of the acid base indicators, they undergo this type of reaction, benzenoid form to quinonoid form. Similarly, in case of benzidine diphenylamine indicator, here also this benzidine undergoes oxidation to form quinonoid form. See, this is quinonoid form, continuous conjugated pi bonds. This is responsible for the color. Therefore, in this case also benzidine is converted into a quinonoid form. So, see, this is the theory, quinonoid theory, which tells about how this color formation, the color indication is there, that is due to benzenide form. So, this is about acid base theory, Ostwald's theory and quinonide theory. And you have acid base indicators, phenolphthalein, methyl orange, parathymal blue, methyl red indicators are there, and their pH ranges are like this. In case of methyl red, the pH range is 3.0 to 4.5. In case of methyl orange, pH range is 4.5 to 6.5. Bromothymal blue 6.5 to 8.5. Phenolphthalein 8 to 10.5. So, an universal indicator is one which is a mixture of several indicators of different pH range, which covers a long range of pH. So, this mixture, if you take these 4 indicators as a mixture, in this mixture the pH range is very large. pH range is from 3 to 11. So, that type of indicators are called universal indicators. Universal indicators are a mixture of indicators which has a wide pH range, that is universal indicator. So, that is about acid base indicators. In detail, this is the explanation about acid base indicators. Now, come to redox indicators. So, there are several types of titrations. The titrations involve acid base reaction, weak acid strong base, weak acid weak base, strong acid weak base, like that, acid base indicator. There are so many titrations which involve other type of reaction. For example, in case of titration between ferrous sulfate and potassium dichromate, there ferrous sulfate undergoes oxidation to form ferric sulfate, whereas potassium dichromate undergoes reduction to form chromium oxide. It is a redox titration. So, oxidation of one reagent takes place and reduction of one reagent takes place. This type of reactions are called redox titration. In these type of titrations, we use redox indicators. One important example of redox indicator is diphenylamine indicator. Diphenylamine indicator is a redox indicator. Here, this indicator also undergoes oxidation or reduction. So, oxidized form of the indicator takes up electrons, it undergoes addition of electrons, that is reduction, to form reduced form. So, reduced form of the indicator. Oxidized form has different color when compared to reduced form. One important example is diphenylamine. This diphenylamine undergoes oxidation to form benzidine. So, diphenylamine has got one color and benzidine has got another color. Therefore, this indicator can be used in the redox titration. Yellow color to orange color changes takes place. That is redox indicator, acid base indicators, redox indicators, and lastly we have adsorption indicators. So, we have so many titrations which involve adsorption mechanism. For example, in the titration of silver nitrate versus sodium chloride, when sodium chloride reacts with silver nitrate, it forms a precipitate of silver chloride. Silver chloride precipitate is formed. As soon as the precipitate is formed, a layer of chloride ion is adsorbed on the precipitate, and then sodium ion is adsorbed as a second layer. Now, when you go on adding sodium chloride, silver nitrate goes on forming the precipitate, and that precipitate chloride and sodium ion, which forms adsorption layer, they undergo reaction with silver nitrate, and there is no sodium chloride to form further silver nitrate. Therefore, when the precipitation is complete, this indicator, fluorescent indicator, gets adsorbed in the second layer, and it goes into the solution to form another color, fluorescent. So, it forms another color. Therefore, after completion of the precipitation, before the completion of the precipitation, it forms one color, because there are sodium and chloride ions which are there for adsorption. After complete reaction of sodium chloride with silver nitrate, there are no chloride or sodium ions for adsorption. In such a case, the indicator gets adsorbed. So adsorbed form has got different color when compared to unadsorbed form. So therefore, this indicator, adsorption indicator is used. So adsorption indicators. Okay. Now come to pH titration curves. Let us see the shape of the curves obtained when acid is titrated against a base. So we have weak acid, strong acid, weak base, strong base. For example, for strong acid, let us take HCl, for strong base, sodium hydroxide, for weak acid, acetic acid, and weak base, ammonium hydroxide. So in the titration of a strong acid against a strong base, you take sodium hydroxide in the burette and take about 25 cc of HCl in the pipette. Now, if you go on titrating HCl with sodium hydroxide, pH slowly changes in the beginning because HCl is a strong acid. It has got very high pH, very low pH. pH value around 2 when you take dilute HCl, 25 cc of dilute HCl. If you go on adding sodium hydroxide, when the volume of sodium hydroxide is added, in the beginning slowly the pH changes because the solution is remains still acidic on addition of sodium hydroxide. On adding more of sodium hydroxide, what happens? Near the end point, the pH suddenly changes. pH suddenly changes from 4 to 10 at the end point. So when you add the volume required for the neutralization of 25 cc of HCl, say for example both of them are DC normal. If both of them are DC normal, it requires 25 cc of sodium hydroxide solution. So when the volume reaches 25, neutralization takes place there. At the neutralization point, pH suddenly changes from 4 to 10. Therefore, there is a long range of pH change at the end point of the reaction, and we have several indicators at this range. Methyl orange indicator has got the pH range 3.2 to 4.5, and also phenolphthalein indicator which has a range between 8 to 10. Therefore, any of the indicators who have got this range between 4 to 10 can be used. Phenolphthalein changes its color from colorless to pink, whereas methyl orange yellow to orange red. Any of the indicators can be used for this type of titration, strong acid and strong base titration. Now, suppose if you come to second type of titration, where a strong acid is titrated with a weak base. Weak base is one which ionizes partially, but HCl is strong enough. So if you take 25 cc of HCl which has very low pH here, as soon as you start addition of ammonium hydroxide, there is no sudden change of pH like this. pH slowly changes here. pH slowly changes. When H plus is completely neutralized by the hydroxide ion, pH sudden jump will be there in the pH, but the pH jump will be there from 4 to 6. 4 to 6. Therefore, the indicator which has got this range of 4 to 6 is methyl orange. So therefore, only you have to use methyl orange. Phenolphthalein range is not met by this rise in pH at the end point. Therefore, methyl orange is the indicator for the titration of a strong acid and a weak base. Now come to next type of titration, weak acid versus a strong base. So weak acid versus a strong base, acetic acid is a weak acid. It undergoes it is a weak acid, it ionizes to a small extent, but it reacts with sodium hydroxide to form sodium acetate, which is a strong electrolyte which ionizes completely. Therefore, you take 25 cc of acetic acid, 25 cc of acetic acid has got pH, low pH, and if you go on adding sodium hydroxide, pH rises. Sodium hydroxide is a strong base. It reacts with acetic acid to form sodium acetate. Therefore, pH changes. At the end point, what happens, you know? At the end point, when acetic acid is completely neutralized, the pH suddenly changes in this range, phenolphthalein range. The range of phenolphthalein indicator is 8 to 10 or 10.5. At that range, there is a sudden rise in pH when you add sodium hydroxide. At the end point, at the neutralization point, what happens? The pH suddenly changes, and this change takes place at the range 8 to 10. Therefore, in this type of titration, weak acid against a strong base, only phenolphthalein indicator is helpful here. So, use phenolphthalein indicator. So, for the titration of a weak acid and a strong base, phenolphthalein is a suitable indicator. For strong acid and weak base, methyl orange is the suitable indicator. Now, come to the last type of titration. In case of a weak acid against a weak base, actually there is no sudden rise at the end point. Since both of them are weak weak acid and weak base, they ionize partially. Therefore, there is complete neutralization will be not there sharply. Therefore, there is a slow change in pH. That slow change in pH is like this, and there is no sudden rise in pH at any of the pH range. There is no range at all in the rise in pH. It slowly changes like this. So, there is no range here. Therefore, no indicator is helpful here. You cannot use any indicator. No indicator. Therefore, a weak acid cannot be titrated against a strong base. Therefore, by volumetric method, you cannot estimate a weak acid against a weak base. It cannot be estimated. Therefore, indicators are not useful here. Therefore, we go for other methods of titration. So, this is about pH titration curve in case of acid base titrations. We shall discuss the calculation of pH for these type of indicators in the next session of video.